All right, we're now starting the subject of spectral theory. And what spectral theory is, it's the study of eigenvalues and eigenvectors and their applications. So this notion is spectral theory kind of as a subject here. And so, of course, that means if we're going to study spectral theory, then we need to start by understanding what eigenvalues and eigenvectors are. So let's start with just an n by n matrix A. So here's an n by n matrix. Let's also consider a vector x that belongs to n-dimensional complex space. And if you'll remember that one-dimensional complex space is the same as two-dimensional real space, well, that means n-dimensional complex space, or space of complex dimension n, is the same or isomorphic to r to the 2n here, right? So Cn, we're thinking about r to the 2n, right? Because when we had n equals 1, well, we were looking at C, which is r2. If you were to look at C2, which this space is a very hot topic in topology, if you ever end up studying topology, which is isomorphic as a space to R4, especially four-dimensional topology. This is a very interesting space, but this notion generalizes for arbitrary finite dimension n here, right? And so what does this mean to have a vector living in this space? Well, that means x is, still x1 through xn, but now where xi is an element of the complex numbers, right? So xi could be like ai plus b. Let's use j, since we're using I to denote our unit imaginary number here. So xj is xj would be equal to aj plus I times b sub j here. Okay, so basically we just have an n-dimensional vector with entries in the complex numbers. And let's say such that, so we want this matrix A and this vector X to be such that there exists a complex scalar lambda with or satisfying that the matrix product A times X is the same as the scalar multiple lambda times X, right? And you may say, well, oh, I could just multiply by X inverse on both sides, and then no, right? Because this is matrix multiplication on one side and scalar multiplication on the other. So this is a very interesting equality, or a very interesting criteria that has to be met here. And so if we have a matrix A, vector X, and scalar lambda such that this holds, then we have a following definition. Then lambda is called an eigenvalue of A, and X is an eigenvector of A associated with lambda, right? So you may have multiple eigenvalues and eigenvectors. For example, you could have like A x1 equals lambda 1 x1, but also for the same matrix A, you could have ax2 equals lambda 2 x2. And in this case, lambda 1 and lambda 2 would be the eigenvalues of A, and x1 and x2 would be the associated eigenvectors, right? Where x1 is associated with lambda 1, x2 with lambda 2, right? We also have a notion of the spectrum of a matrix. And this is where the notion of spectral theory comes from. So here's another definition. Let's define sigma of A to be the set of all complex scalars, so lambda and C, such that lambda is an eigenvalue of A, right? Then sigma A is the spectrum of A. So it's the subspace of eigenvalues of a matrix. This is called the spectrum of a matrix. Okay, or a priori, we don't know that it's a subspace, so let's just say subset, right? Okay, so let's see an example of a matrix along with some eigenvalues and eigenvectors, right? And we know those necessarily satisfy this AX equals lambda X. This is, I want to emphasize the importance of this equation here. This is very important, right? Because this contains the information, given a matrix A, this contains the information of the eigenvalues and the eigenvectors. And what we'll learn is it actually contains information about how to solve them as well, like just from this equation. So I really want to stress the importance of having this memorized and understanding what this relatively simple equation, while simple at the surface, but it's very, right, it's simple but not easy, right? How much information such a simple equation can contain here. So let's look at an example. Let's say A is the 3x3 matrix with the first column of zeros, and then 5, 22, -9, then -10, 16, -2. So here's our 3x3 matrix. Now let's look at the vector x1, which is given by -5, -4, 3, and x2 is given by 1, 0, 0. Okay, so let's compute the product AX1 here. Well, this is going to be 0, 0, 0, 5, 22, -9, -10, 16, -2 times the vector -5, -4, 3. If we compute this product, well, in the first term, looks like we're going to get -20 minus 30, so that's -50. In the second, or not term, excuse me, in the first component. In the second component, it looks like we're going to get -88 plus 48, which would be -40. And the third component, it looks like we're going to get 36 minus 6, which is +30. And if we pull out the 10 that all of these components have in common, then this is 10 times -5, -4, 3. And so here, this would have an eigenvalue of lambda sub 1 equals 10, right? Because what did we do? We just found, or we have this equation that says AX1 equals lambda 1 x1, right? These are necessarily the same vector. And on the left-hand side of the equation, we're multiplying by a 3x3 vector. But on the right-hand side of the equation, we're just scaling this vector, right? And so that's really a pretty interesting concept, that you can have this instance of when multiplication by a 3x3 matrix is actually just scaling a vector, right? And there's some notions of geometry there that you should think about. It's like, what would it mean for the multiplication of a matrix to just be acting as scalar multiplication, right? That's a pretty interesting concept geometrically as well as algebraically. So what about the next one? Let's look at AX2, right? Well, this is A, which is 0, 0, 0, 5, 22, -9, and then -10, 16, -2, and then times 1, 0, 0. Well, you may notice right away, the matrix multiplication is going to give us the 0 vector, right? And so because of this, well, we actually notice that 0 the 0 vector is 0 times 1, 0, 0, right? And so we get actually the lambda 2 here is 0. And here again, we have our AX equals lambda x. Well, in this case, we have a 0 eigenvalue and an eigenvector of 1, 0, where again, these vectors are necessarily the same, right? This is the equation ax2 equals lambda 2 x2, just as this equation was ax1 equals lambda 1 x1, right? And so this is an example of eigenvalues and eigenvectors of the matrix A, right? We would say the eigenvalues of the matrix A are 10 and 0, and the eigenvectors, or the basic eigenvectors, are -5, -4, 3, and 1, 0, 0, right? You may notice that if you have an eigenvector, like in this case, we have the eigenvector -5, -4, 3, right? Well, this equation would still hold if you multiplied both sides by any scalar, right? So actually, we would have like x1 of t, which is, use like -5t, -4t, and 3t. And this is an eigenvector for all t in R, right? And so you have an infinite number of eigenvectors here to a given eigenvalue just by scaling this, right? Well, if you scaled this on both sides of the equation, certainly the equality would still hold, right? You're scaling a vector on the left-hand side of the equation. Well, you have to do that on the right-hand side of the equation for it to remain an equality. So similarly here, right, we would have that t 0, 0, like maybe x2 of t. This is an eigenvector for all t in R as well. So if the eigenvalue is 0, we have an infinite number of eigenvectors. But this is the notion of, you'll see here, we take like the simplest integer solution here, and that's called our basic eigenvector, right? So the 5, -4, 3, and then the 1, 0, 0, these would be our basic eigenvectors. Even though those span like a subspace of eigenvectors, right? Like a solution space here. Okay, now the question would be, how do we find these, right? In this example, we had a 3x3 matrix A, and then I gave you the two vectors. I said, here's x1, here's x2, right? Well, in the wild, when you come across a matrix in the wild and you have to find its eigenvalues and eigenvectors, you're not going to be given either of them, right? Here I gave you the eigenvectors, and then we found, well, a priori, I gave you two vectors to just take the product of these vectors with A. We found out that this is actually an eigenvector, and then we found the corresponding eigenvalue, right? Well, when you're lost in the wild someday and you come across a matrix A, you're not going to have either the eigenvalue or the eigenvector, right? So the natural question, or the question of survival here, is how to find eigenvalues and vectors, right? Okay, well, let's start by just understanding the definition, right? We know that eigenvalues and eigenvectors must necessarily satisfy this equation, that AX equals lambda x, right? For a fixed matrix A, and then for some scalar, complex scalar lambda, for some complex vector x. Well, this is the same. Let's subtract lambda x to both sides. We have ax minus lambda x is 0, which means, notice there's an x in common here, and we know matrix addition and subtraction is distributive, so we could factor out this x, and then that would lead to a minus lambda times the identity, right? A minus lambda I times x equals 0. And let's multiply both sides by -1. And so we get lambda I minus a times x equals 0. And so now what we would have is that solutions to this equation here give basic eigenvectors for a given, or corresponding, appropriate, whatever, for a given, let's say corresponding lambda, right? So if you could find this lambda, then you would know how to find the corresponding eigenvectors based on the solutions to this equation. But then you would ask yourself, well, how do I find lambda, right? Well, what do we need? We need, so now the question would be, okay, I can find an eigenvector given an eigenvalue, but how do I find an eigenvalue? So how to find lambda first? Well, let's see. How would we do this? Let's consider the equation. And I should have mentioned here, maybe it's really important that it's very important that here x is, and I'll put this in red to, this is a non-zero vector, right? We do not have eigenvectors that are given by the 0 vector. So we are always looking for a non-zero x, right? So what does that mean with this emphasis that you can never have, and I'll make a remark here to emphasize the importance. Eigenvectors are always, or must be, let's say eigenvectors must be non-zero, i.e. x is not 0, right? So why does this come into play when we're trying to find lambda? Well, if we have lambda I minus a times x equals 0, you may notice if the matrix lambda I minus a is invertible, then this implies that there exists an inverse. And if there exists an inverse, we could multiply both sides of this equation on the left by the inverse. Then we could take lambda I minus a inverse times lambda I minus a times x equals 0, right? Because multiplying on the right-hand side, anything by 0 will just give you 0. And then we have, by the associativity of matrix multiplication, you could group this product where you take I lambda minus a times its inverse first, and this gives you that x equals 0. But this is a contradiction because we specifically require that eigenvectors must be non-zero, right? Here we are. So what does that mean? That means our assumption that lambda I minus a being invertible was a bad assumption. So if lambda I minus a is invertible, then, and that leads to a contradiction, that means we must have that lambda I minus a is singular. So i.e. must have lambda I minus a as a matrix is singular. What does it mean that lambda I minus a is singular? That implies that the determinant of lambda I minus a is equal to 0. And solutions of this equation, right? This is a scalar equation. When you take the determinant of a matrix, your answer is a scalar, right? It's a number. If there's a variable, it's a polynomial, right? But the point is, it's a scalar. So solutions to this solve for eigenvalues. And this is called the characteristic equation. Okay, so to find lambda is the same as to find solutions, or let's say to find, solutions to the characteristic equation. Okay, so if we have the determinant of lambda I minus A equals 0, this is our characteristic equation. Values lambda that satisfy this equation, these are your eigenvalues. Okay, we also call the entire thing is the characteristic equation. If you want to look at just the left-hand expression here, this is called the characteristic polynomial. So you may also understand the eigenvalues of a matrix as being the roots of the characteristic polynomial. So we could also say, here's a remark, the roots of the characteristic polynomial that lambda I minus A are precisely the eigenvalues of A. Okay, the roots are going to be, right? What's the root of a polynomial? The root of a polynomial, or a root of a polynomial, is a value such that when you plug it into the polynomial, you get 0, right? Well, this determinant of lambda I minus A is going to be some polynomial. Set it equal to 0. That gives us the characteristic equation. Solutions to this equation are in a bijective correspondence with solutions or roots of the characteristic polynomial, which is in bijective correspondence with the eigenvalues of A, right? So this is a very important equation in spectral theory, because this helps you find eigenvalues. And then once you have eigenvalues, you go back, and once you're given an eigenvalue, you come back to this equation here, plug in the eigenvalue that you've calculated, solve for x, that's the corresponding basic eigenvector, right? So it seems like a lot here, and there is a lot here, but examples help. The more you do examples of computing eigenvalues and eigenvectors, the less foreign and less scary this becomes. Okay, so let's figure out, before we do some examples, let's kind of write down a procedure or algorithm on how to find these, right? I've kind of derived this algorithm in these past few slides here, but let's actually write this down kind of succinctly or nicely. Let me write what I've said as a theorem first. So a theorem, let's let A, this is going to be an n by n matrix. And suppose there exists a complex scalar lambda such that the determinant of lambda I minus A equals 0. Then lambda is an eigenvalue of A, and there exists a vector x, a non-zero vector x in Cn, and I could even say Cn without the 0 vector, right? That's what it would mean. So let's say there exists a non-zero n-dimensional complex vector x such that Ax equals lambda x. Okay, and so This theorem here, I'll star it because it's important. This is telling you exactly how to find eigenvalues and eigenvectors, right? So let's look at the procedure. And then in the next video, I think I'll split after the procedure to finding explicit, like calculating eigenvalues and eigenvectors for explicit examples. Okay, so here's the procedure. First, we find eigenvalues of A by solving for all lambda solutions, and that's wordy, by solving the determinant of lambda I minus A equals 0, right? They're, depending on the degree of the polynomial, determinant lambda I minus A will dictate how many eigenvalues you have, right? So if you have a quadratic characteristic polynomial, then you'll have 2 eigenvalues. If you have a cubic, you'll have 3, right? Et cetera, et cetera. This is by the fundamental theorem of algebra. We're guaranteed as many roots as the degree of the polynomial. The second step is then to, for every lambda that we've just found, we find the basic eigenvectors that satisfy lambda I minus A times the eigenvector X equals 0. And then here there's kind of a ghost or phantom step 3, and it's to check that AX equals lambda X, right? And can I use purple? I'll use purple as like a phantom or a light blue, I guess, not so much purple, as this is kind of a phantom step, right? You don't really have to, but you should. You should always check that your computation did in fact give you an eigenvalue and an eigenvector. Okay, so what I want to do next is I'm going to stop here, and then the next video will contain some examples of going through this procedure, and then a little bit on similar matrices. And we'll see how computing eigenvalues and eigenvectors can be simplified using similar matrices.